Okay, welcome to exercise 1 on page 113 of the workbook. This is the Shakey's Pizza problem, so you're going to learn about a little bit of Rapid City, South Dakota culture here. This was the city that I went to college in, and this restaurant I actually spent a lot of time in as a college student. And all I can say is if you ever get a chance to visit Rapid City, check this restaurant out. It is a very unique dining experience, and I will leave it at that. Okay, so what are they telling us in this problem? Well, they're giving us some statistics about people who eat there and don't eat there. So in particular, you can kind of read the second statement here and get the percentages that we're working with. This is going to be a problem similar to the first exercise that we did. And the first part of it asks us to set up a stochastic matrix to model this. Okay, so again, a stochastic matrix just is a way of representing how population is migrating from one state to another. Okay, so I would like to think of this as maybe two states, or what's happening one week and what's happening the next week. Okay, and we're going to be building a 2x2 matrix here. And they're going to be kind of two states, people who eat there or don't, 1 week, and they're going to be transitioning into those same states a week later. Eat and no eat. Let's call our matrix P. And actually we should give names to the two categories that we have. Let's maybe sneak that over to the right here. So how about if we let xn and yn be the people who are eating there or not eating there respectively? And we'll do it in thousands just to make the numbers a little smaller. Okay, sorry, space is a little bit tight here. So yn is thousands who don't eat. All right, so what that means then is that we're going to keep that order in mind as we fill in the entries in our matrix here. All right, so first observation that we might make is that 5% of the people who eat there 1 week will eat there the next week. So as a percentage, that means that we've got a 0.05 here. And the other 95% who eat there 1 week are not going to eat there the next. That puts a 95 down there, 95%. Okay, and then we've got this 2%. That's describing the people who start out not eating their 1 week but do the next week. So that's actually going to put a 0.02 up here. We're going from the no eat to the eat category, and the other 98% are going to be down here. Okay, so there's our modeling matrix, okay, that's describing how we're migrating between these two categories. All right, now that we've got that set up, we're in a position where we can answer part B. So suppose that 5,000 of the local population of 4,000 eat at Shakey's on a given week. Okay, well, if we put that into the language of the xn and the yn that we talked about above, it's giving us a value of x naught. 5,000 would be 5, since we chose to measure our population in thousands. Okay, and then y naught would be the other 35,000 in Rapid City, so that's 35. Okay, and to calculate the populations after 1 week, we're going to take the initial populations and multiply by our stochastic matrix. Notice that the x naught y naught is 535. And now it's up to us to just do the multiplication here. You can double check my arithmetic on this. We're going to get a 0.95 up here and a 39.05 down there. So what is this telling us? Okay, well, above, the first row should be about the people who are eating there, and the second row is about the people who aren't eating there. And they would like how many people do eat there. So we're actually interested in the first number that we see up here. And remember that that's in thousands of people. So 0.95 thousand would really be 950. Okay, and that should be our answer to part B. So moving on here, the next question that they ask us is about what's happening in the long run. Okay, so that's about what's happening as n goes to infinity. And if you attempted this problem, you might have approached this the same way that we answered that same question for the example that we did together earlier. That's a perfectly okay way to do the problem. You can diagonalize the matrix and you can take the limit as n goes to infinity, and that's going to lead you to a correct answer here. But there is a shorter, sneakier way of doing this problem. Okay, remember that what we're really looking for here is the steady state. We called it Q on the previous page. So we are looking for a solution to this stochastic equation that has this form. The steady state population, the distribution of people who do and don't eat at Shakey's, should satisfy the equation PQ equals Q. And so a shorter way to figure out what the long run population is to solve this equation for Q. If we take the Q on the right-hand side and subtract it over to the left-hand side, we can rewrite this equation like this. You might remember this little algebra technique when we first started talking about eigenvalues. Notice that if you subtract on the left-hand side, you get PQ minus IQ, which is just PQ minus Q. That's equivalent to the equation that we just wrote down. And this is a matrix equation that we can solve. All right, so our matrix looks like P minus I. So it would be like taking the matrix P that we have above here and just subtracting 1 from the main diagonal elements. If you do that, 0.05 minus 1 is minus 0.95. 0.02 stays the same, 0.95 stays the same. And 0.98 minus 1 is minus 0.02. There's the system that we're solving. To make it a little bit more manageable, we might choose to multiply through by 100. It just makes the numbers look a little bit nicer. And then notice that if we add the first and the second row, we get a row of zeros. So there's actually a free variable here. We've got one pivot position right there. And we can see that x2 is our free variable, so we'll let it be t. And if you take the first equation here and just do the algebra and solve for x1, I'm just going to show you what you should end up with, 2 over 95t. You can double check that. All right, so our solution to this then looks like Q equals x1, x2, and let's just read off those two entries. So x1 is 2/95 t, and x2 is t. And t can be anything because it's a free variable. Okay, but here's the thing. In our problem, we know what the total population of Rapid City is. It was 40,000 people. And this vector that we're looking at here, if you add the two entries together, they have to add up to the total population of Rapid City. Those are the two states that we were talking about, were people eating at Shakey's or people not eating at Shakey's. So we know then, for this problem to make sense, those two entries have to add up to 40. Okay, again, because 40 is the total population. And so that gives us a way to solve for t and find one value of t that makes sense in our problem. So if you do the arithmetic on the left-hand side, 2/95 t plus t, that's actually 97/95 t is equal to 40. And I'll leave it to you to verify that if you solve that for t, you're going to get 39.175. Okay, and therefore, if we go back up to the form of Q here and substitute in that value of t, we're going to get the actual population distribution here. So the t in the second coordinate, that's just going to be exactly the 39.175. You can do the algebra in the top coordinate and confirm that up there you're going to get 0.825. Now, which number are we interested in this problem? Well, they asked us how many people do eat at Shakey's in the long run, and the number of people that do eat is given by the first entry. And so that should describe our answer. Remember that that number is in thousands, so 0.825 thousand people would really be 825 people. Okay, and I believe that we have answered all of the questions that they asked us.